Hi there, I would like to present our paper Fast and Furious Convergence Stochastic Second-Order Methods under Interpolation. This is joint work with my collaborators Sharan, Isam, Mark, and Simon. In optimization for machine learning, first-order methods are popular for their cheap iterations, but they can suffer from slow convergence on ill-conditioned problems. On the other hand, second-order methods converge faster by explicitly adapting to the local curvature of the objective. On a quadratic function, Newton's method converges in just one iteration, whereas gradient descent takes a zigzagging path. The plot on the bottom shows different types of convergence rates. First-order methods are usually in the linear or sublinear regime, whereas Newton's method is able to achieve the fast quadratic convergence in a local neighborhood. However, forming the Hessian and computing the update direction can be quite expensive. A natural approach to reducing the cost of forming the Hessian on a large training set is to use subsampling, similar to SGD, but convergence can be slowed down due to the noise in the update direction. In this work, we consider overparameterized machine learning models that satisfy the interpolation condition, meaning that they can completely fit the training data. Examples include logistic regression on linearly separable data, nonparametric regression, boosting, and overparameterized neural networks. The motivation here is that subsampled first-order methods can converge faster under interpolation, and therefore the question that we would like to address is what's the behavior of subsampled Newton's method in this setting? We consider the unconstrained minimization of a finite sum objective where each fi is twice continuously differentiable and n is the number of training examples. We assume that f is mu strongly convex and L smooth, implying that the Hessian has eigenvalues bounded between mu and L. We define constants mu bar and L bar as the average strong convexity and smoothness constants over the training set, whereas Ls and mus are the corresponding average constants on a subsample. We denote the worst case constants by mu tilde and L tilde, and note that while the overall strong convexity constant mu needs to be strictly positive, the worst case constant mu tilde on a subsample is allowed to be 0. The interpolation condition means that the gradient of each individual component is 0 at the global minimum, and for a smooth, strongly convex finite sum objective, this implies a strong growth condition, which just says that the size of the individual gradients are always upper bounded by the size of the full gradient in expectation. The rho here is a value greater than 1, and in this case, it is just L over mu. Let's begin with the usual SGD update given by this expression. So here, eta k is just the step size. This gk here is an index set chosen uniformly at random. And the subsampled gradient is computed by simply taking an average of the individual gradients within a mini-batch. And the regularized subsample Newton update, abbreviated as RSSN, is simply taking the inverse of the LM regularized subsampled Hessian as the preconditioner. So here, SK is another uniformly chosen mini-batch independent of the gradient mini-batch, although this independence assumption is only needed for analysis, and in practice, we can use the same mini-batch. The LM regularized subsampled Hessian is computed similarly by averaging the individual Hessians within a mini-batch plus a small diagonal to ensure positive definiteness, so the update direction is well defined. Our first result is on the global convergence of RSSN. Similar to SGD, we show that the interpolation condition allows RSSN with a constant batch size to obtain global Q-linear convergence. Assuming the function is mu strongly convex and L smooth, and that the regularized subsampled Hessian has eigenvalues bounded in this range, then under the strong growth condition, RSSN with a constant batch size converges at a Q-linear rate, where the rate is characterized by this constant alpha. If we take the mini-batches to be the entire training set and apply 0 regularization, we can actually recover the deterministic rate. And in the absence of interpolation, one needs to geometrically increase the gradient batch size to obtain only an R-linear rate, which is a weaker notion than Q-linear. Our next result characterizes the local behavior of RSSN. We show that with interpolation, RSSN converges with a linear quadratic rate in expectation with geometric batch growth. So under the same assumptions as Theorem 1, with the additional Lipschitz continuity of the Hessian, bounded moments of the iterates, and bounded variance of the regularized subsampled Hessian assumptions, RSSN with a unit step size and growing batch sizes satisfying these conditions converge in a local neighborhood at a linear quadratic rate. The constant C2 here on the linear term of the rate is between 0 and 1, which guarantees contraction, while the constant C1 on the quadratic term just needs to be finite. The growth rate for the subsampled gradient is actually the same as what's required to obtain linear convergence by SGD without variance reduction or interpolation, and the growth rate for the subsampled Hessian can actually be an order slower. In the absence of interpolation, SSN can only achieve an asymptotic superlinear rate with batch size GK growing faster than geometric. This asymptotic superlinear rate just means that if we run the algorithm for a long time, eventually it will be faster than linear. But this can also just be arbitrarily close to linear. An interesting corollary of the previous result is that if we decrease the LM regularization proportional to the gradient, RSSN can achieve a local quadratic convergence similar to Newton's method in the deterministic case. And this decay rate is in fact inversely proportional to the growth rate of the subsampled Hessian, which means that larger batch sizes require smaller regularization, and it makes sense because our overall objective is strongly convex, and thus as we increase the batch size, the subsampled Hessian will be more likely to be positive definite, and thus less regularization is required. For the experiments, we consider logistic regression on synthetic linearly separable datasets such that interpolation is satisfied. We consider two variants of RSSN, one with constant batch size and one with a geometrically growing batch size. We use a Hessian-free implementation that utilizes inexact conjugate gradient with a regularization parameter that decreases as the batch size grows. We compare against several first-order methods such as SGD and its accelerated version, SVRG, ADAM, and ADAGRAD. We also compare against the deterministic unregularized Newton's method. And all second-order methods here use stochastic line search from Vaswani et al. To select the step size, which has been shown to be effective in the stochastic first-order scenario. In these plots, on the x-axis, we have the epochs, while the y-axis are the training loss in log scale. The number in the title of each subplot is the margin of linear separability of that particular dataset. We observe that all second-order methods significantly outperform first-order methods, and in particular for RSSN, global convergence can be achieved using only a constant batch size, as indicated by the red curves. And the purple curve that uses a growing batch size shows a faster convergence than using constant batch size. And finally, as we increase the margin, the problem becomes easier, and second-order methods also become more stable. In our paper, we also have logistic regression experiments on real datasets under an RBF kernel, and in those experiments, we draw similar conclusions and present runtime plots which show that with the Hessian-free implementation, stochastic second-order methods are competitive in terms of the wall clock time as well. Additionally, in the paper, we also have results on RSSN under self-concordance, as well as stochastic BFGS methods for smooth and strongly convex functions, both in the interpolation setting. Here are the links to our paper and code, and thank you for watching.